So here's the last problem we're going to look at. This closes out the course. This is a former exam problem that did not go well. So what do we have here? We have a compactor which has the frame here, is 5,500 kilograms, center of mass at G. So if we look at what we have then, is in the front there's a great big heavy roller that's helping to compact everything. That has a mass of 200 kilograms. Radius of gyration of 0.45 meters. We'll note the actual radius is 0.6 meters. Okay, this compactor is driven by these rear driving wheels. Okay, and notice they're conventional tires. And we're told there is a torque applied to this back axis of 600 Newton meters. All right, and we're told no slipping occurs in either place, and we should neglect the mass of the driving wheels. This is going to be huge. And why would they do that? Okay, well, this big roller is probably like loaded with water or something, so that's just solid. All that steel, and then you got these tires in the back. Compared to everything else, they're zero. Basically where that's coming from. So, and as we look at this problem, it says, in doing the problem, I tried to guide the students to help them do better. Did not guide them enough. So here it says, first off, at a minimum, draw free body diagrams for the rear driving wheel and the front roller. The process of doing those two leads you to do this part, hopefully. So let's take a look at that. So here's the rear driving wheel. And so what we have, so here's the wheel. And so we have this 600 Newton meter torque driving it forward. Certainly the frame is going to be pushing down here, dy. And as the moment's applied here to push this whole frame together, the frame will eject, so I have dx pushing back. All right. Now as this torque is applied, it's trying to drive the wheels clockwise. Okay, slide them through. So friction is going to object to that, and it'll push back. So we have force of friction here, and here's the normal force on the ground. Now, the moment that I say this goes backwards, well, it means then it goes forward, pushing the frame. Now, I'll note that pushing the frame forward here is actually going to, given this, it's the negative x direction. All right, so dy goes down here. It means that that's pushing up in the frame over here. Here we have mass and weight of the frame. Likewise, when we get to the front roller, the roller will be holding up the front of the frame, and the roller, as this thing pushes forward, will be ejecting, so I have ax pushing back against the frame. So now I move to the front roller. The frame will be driving the front roller forward. The frame will be coming down on the roller, so there's ay coming down. Here's the weight of the front roller, 2,000 G. Normal force from the ground. And then we'll note this roller is just free to move. So what makes it rotate? Because you got to have a moment somewhere. What's the force of friction? We'll then drive it to go around and around and around. Okay, so we've done that. Now let's look here. Part 2, it says, analyze the assumed massless rear driving wheels to determine the forward traction force. All right, so let's move this up a little bit so we can see that and do it. So, massless wheels. So let's take the moments about D. All right, so if we do that, all we have is force of friction and this, what the engine's applying, this torque. So torque's going counterclockwise at 600 minus force of friction would be driving it clockwise times 0.5 radius of the tire equals Ig alpha. But the tires are massless. This is important. Okay? All this other mass is not connected. we've taken it away and replaced it with these forces. So we have the sum of the moments from through the various forces and the torque applied equals Ig alpha. But there's no mass there, therefore Ig is 0. Alpha is not 0, but Ig is. Okay? Well, if Ig is 0, then we can solve for the force of friction. We get, bring the force of friction times 0.5 to the other side, divide through the 0.5, we get force of friction is 1200 newtons. Okay? Well, now we can sum the forces in the x. So, sum of forces in the x, we have dx going forward, force of friction going backwards, which relative to this is actually forwards. But so dx minus fx equals mass times acceleration. But mass is 0. Okay? Acceleration won't be, but mass is. All right? So solve. It says dx is 1200 newtons. So now we have 1200 newtons as being the driving force going into this frame. Okay. Well, once you've done that, that kind of starts pushing you along the line of with forces. So the next thing I did is I said, well, this is coming along with 1200 newtons. So sum the forces in the x. I have ax minus dx, because remember, x is to the right, positive, equals mass times agx. Well, we know what dx is, 1200, so I just substituted that in. And that's what we have here. All right, now let's think about this. We're always having to do kinematics, so we know when we look at what's happening here, whatever the acceleration is here along the x, how does that relate to what's happening here? All right, let's relate it to what's happening with the roller. All right, and that's what I have note here. Whatever the acceleration in the x here is the frame, you'll have clearly the same acceleration here at point D and the same acceleration at point A in the x. This is what I'm taking note of. Focusing on the roller, but the same would be true in the back. So here we have a roller x equals agx. What is a roller in the x? Well, since we're rolling out without slipping here, it would be alpha the roller cross r, 0.6y going up, which is minus 0.6 alpha right here in the x. So agx is going to be minus 0.6 alpha of the roller. All right? So, a little bit of kinematics, anticipating as we make the move this way. All right. So continuing with this problem. What do I do next? Lots of information. Well, I've analyzed this piece. I've started going across, and this thing isn't moving in the y, so the sum of forces in the y will be this minus that equals 0. Not exactly exciting. Okay. So let's go over here and take a look at this point B down here. And so I'm analyzing forces. Let's just stay related to Newton's law. And so what I have here is summing moments. All right. So let's see. If I sum the moments at B here, I only have one, AX relative to B. So that would be R cross F coming in here. So that's going to be a counterclockwise. So we have 0.6 AX for the torque associated with AX. And then after that, everything else relative to B, force of friction does nothing. No moment. All right. So there's the only torque. And then, so here I would then follow that up. Whoops, this is getting out of range. That's equal to Ij alpha. Okay. Plus R from B to A cross mass times acceleration of G. Or just plain A. Okay, center of mass here, whether or center of mass of the roller, they're all rigidly connected. They're all going to be going at the same acceleration. All right. So what I did here then is so I have that IG. Well, that's just mass is 2,000, radius of gyration of the roller 0.45. So I can substitute into that there. Times alpha. And then R from B to A is 0.6y cross mass times, and here's our acceleration. Okay? And if I multiply all this out, it want 0.6 AX is equal to 1125 alpha. All right? So, or bringing the 0.6 to the other side, AX is 1875 alpha. This is a very helpful equation. Why? Because I'm trying to, here I have AGX. I can relate AGX to alpha, and I can relate alpha to AX. All right. Well, that's really useful because look over here. Can we see that? Yeah, we can. AX minus 1200 equals 5500 AGX. So I can substitute for AX in terms of alpha, and AGX, I have that in terms of alpha. Now I have, that'll give me one equation, one unknown. And that's what we have here. So I took this equation, substitute, got it all in terms of alpha. And so here we have, on the front roller, the angular acceleration. No problem. Multiply through to get AGX. So here we have minus 0.1391 meters per second squared. So it's going this way, which makes sense. And we can, using alpha, we can then get AX is 434.8 newtons. So we know our forces now. So the last thing we're asked, now that we know our forces, we could apply those forces for 4 seconds, and we can use momentum to finish this out. There's 2 ways you can go about this problem from here. All right? I'll show you the easy one. All right? So let's just move this over and let's make sure we can see the parts here. So, looking here, all right, so we're looking at the frame. We can look at the frame relative to linear momentum. What's the initial momentum? Velocity initially started from rest, so it's 0. Then the set question is, what forces were applied? We knew dx was 1200. We now know AX is 434.8. All right, so we had 434.8 actually pointing back, 1200 pointing actually forward, times 4 seconds. Fixed forces for 4 seconds equals mass times velocity after 10 seconds. Solve. V2 is minus 0.5565 meters per second. It's going that away. So, with all of this nonsense going on here, we didn't actually have to apply angular momentum. That being said, we could still do it. And so that's what we have here. If you go back to point B here, the initially with the roller, and that's what we have here. Make sure this is all visible. There we go. So this starts from rest. So initially omega is 0 for the front roller, and the velocity of the center of mass of the roller is 0. Done. All right. External moments. All right. What do we have? Relative to B, we just have one. AX, okay, 0.6 meters for the radius, 4 seconds when we go to integrate this, right here. So there's the integral. So there's that part. Initial angular momentum, the integral of the moments, external moments at B, and then we have the final angular momentum. And so now we have the final part here. HB2, so here is 20 times 0.5 squared. That's the mass moment of inertia for the front roller, times omega, which we want to find. And then we would have, going back, let's bring the front piece in, we would have, going from B to A, R cross VA here. Okay, so VA2, this after applying the moment. So 0.6y cross, and here's the velocity, minus 0.6 omega. So we have our three terms. We could solve for omega, we would get this. Multiply by r, we have the same V2. Much more work to do here. Still gives the same answer. Much better way to go. All right. If you have questions, let me know. But this is it. We have finished the lectures for the course. I wish you well. Bye now.